So welcome to the very first of our Pages 2K seminar series. This is a new seminar series that we started with the goal of really just bringing together the Pages 2K community and people who are involved in Pages 2K already, as well as folks who are not. My internet is unstable, so if I am breaking up, someone wave at me frantically and I'll just stop talking. So our very first seminar of our series is going to be given by Thomas and Diana Vladimirova. So I will quickly introduce them and then they can go ahead and get started. So Thomas is a paleoclimatologist and head of the ice core research group at the British Antarctic Survey. In addition to drilling ice cores, Liz and her team produce high resolution chemistry, isotope and gas measurements to reconstruct past climate variability over decadal to millennial timescales. Her recent research focused on reconstructing Antarctic surface mass balance and developing new proxies for past wind strength. Liz had been involved with Pages for many years, contributing to the Antarctica 2K project, and now leads the Clive-Ash 2K project. Diana Vladimirova is a postdoc at the British Antarctic Survey. She's primarily interested in high resolution ice core measurements and paleoclimate reconstructions based on greenhouse gases, stable water, isotopic, and chemistry records. And so how this is going to work, I'll hand the over to them in just a minute. They'll go ahead and give their talk. For any of the people who are here live right now, if you have a question, you're welcome to type in the chat that you have a question, or you can just type your question in the chat. You're also welcome to just wait until the end, and then we'll do the same. We'll handle the Q&A in the same way after that. Do also, there are still people present right now, but most of our audience is going to be participating asynchronously, watching this talk in whatever time zone that they're in that makes sense for them. If there are further follow-up questions, then you're welcome to get in touch with Liz and Diana directly. So I think that's it. Are there other logistics, Oliver or Sarah, that I should be thinking about? I assume not. So go ahead and get started. Thank you.
All right, thank you. I will start by sharing my screen. Okay, hopefully everybody can see that. So yeah, thank you for the invitation and for the opportunity to present some of the work that the Clive-Ash 2K group have been doing. And I'm honoured to be the first one in this new Pages 2K seminar series. So this work is a combination of, so it's myself and Diana that are going to be presenting this, but it's also just to be aware that this is representing the community as a whole. So there's various different people who have been involved in different aspects. So I'm going to start this talk really from where we kind of started, which was taking over from the previous phase 2 of the Pages 2K network. So I'm going to start off with reviewing the synthesis that we produced from that, and then really taking it on and highlighting some of the great new work that was generated from that that's been undertaken by the Clive-Ash group, but also by the wider communities. I'm just going to kind of review some of that. And then I'm going to move on to talking about one of the products that the Clive-Ash group has worked on, which is a review of sea ice reconstruction spanning the last 2,000 years. And then to finish off, I'm going to hand over to Diana, who's going to tell you all about the exciting new data compilation that we're working on. So hopefully that will make sense as to why it's snowfall, sea ice, and salty snow. So at the beginning of this, we took over from the regional groups, and so I was involved with the Antarctica 2K project. I'm just putting up here to show the 2 compilations that we produced as part of that. So under that initiative, we were kind of invited to contribute towards the regional surface temperature and precipitation reconstructions. And for Antarctica, that works out for us as stable water isotopes and snow accumulation. And in that first data compilation, it was very much looking at what the published records were and trying to pull that data set together. And just one thing to kind of point out, something that Barbara Stenny, who led the isotopes, and I led the snow accumulation work, was the kind of differences in what records were available. And so for the isotope compilation group, they had 112 records submitted. Of those, 26 were not actually stored in a public data center, so the data had to be requested. Whereas for the snow accumulation, we had much less records available to us. So we only had 79 records, and of those, 23 were not stored in a data center. And this was just quite an interesting thing to highlight, really, because all of those isotope records have to have an age scale. And if they have an age scale, it means they've got a snow accumulation. And so what this kind of highlighted quite early on was actually that there wasn't so much scientific value placed on the snow accumulation records. And so that's something I've kind of set out as my personal quest to try and improve that situation. So just highlighting some of this is the original work from the 2017 papers. So for the isotopes, this was the compilation of all the ice core isotope records and then put into these regional composites. And for the isotopes, there was various methods that they used for scaling this. So the figure here is showing this as a temperature anomaly. But what this really highlighted is the regional differences and why it was so important that we're looking at regional scale, not just continental scale. And so that we can see that over the last few hundred years, there's been this kind of significant warming trends have been identified. But really, it's only, although there is warming occurring around some of the coastal regions, it's really only the Antarctic Peninsula for which this warming is actually significant. So this was quite a sort of key thing showing the importance of the regions. And this is also followed through again in the snow accumulation compilations. So this was my contribution to the Antarctica 2K, was compiling all the records, and we had a total of 79 ice cores that we were able to gather. And for the ice core snow accumulation, it was really important that we sort of separated out the different geographical regions, but also separated out on elevation. So what we wanted to do is make sure we kept the high accumulation coastal zones separate from the low accumulation central plateau regions. For the snow accumulation, we were able to sort of convert this to precipitation, if you like, by comparing it with the precipitation from the reanalysis data, and also convert this into gigatons of surface mass balance by comparing this with the regional atmospheric climate model. So we used RACMO. And again, the thing that sort of stands out here in the last few hundred years is that there has been kind of variability. So we've got this pattern of increased snowfall in the peninsula and then a reduced snowfall occurring in West Antarctica. But again, it's only really the Antarctic Peninsula that sort of stands out as this particularly significant region. But for the different regional records, but when we're actually combining these together, what we found, which was somewhat somewhat unexpected, is that actually across the whole of the Antarctic ice sheet, we've seen quite a significant increase in surface mass balance or snow accumulation since 1800. So in the equivalent of 272 billion tons worth, more snowfall was falling in the decade from 2000 to 2010 was falling in the decade 1800 to 1810. And so that's quite a huge number, but just to sort of put that into context, that's the equivalent of twice the volume of the Dead Sea. So obviously these very large changes in snowfall have quite an impact on a very direct and measurable impact on global mean sea levels. And so the figure here from the work I did with Brooke Medley is where we've converted this change in mass, so the amount of snowfall, into actually the sea level mitigation. And what we were able to show is that during the 20th century, this additional snowfall that fell on Antarctica actually mitigated global mean sea levels by 10 millimeters. So that's to say if this snow had fallen anywhere other than Antarctica, where it becomes locked away, sea levels would have been 10 millimeters higher. So just it's important whenever I kind of present anything about this snow accumulation changes, it's important to put this into context of the mass loss that we're also experiencing. So we know that Antarctica is losing mass. And so just to sort of put it into context, that the amount of snowfall that's been falling isn't actually enough to compensate for the mass loss. We're still out of balance. So the initial synthesis, as I've sort of presented, they themselves were a pretty big contribution to our understanding of what's going on in Antarctica. But one of the things that's been really exciting to be involved with and to see is actually how much new research has been generated from this. So not just within the people involved with Clevash and Pages, but also with the wider community. So over the next few slides, I'll confess, I've just cherry picked some of the studies that I'm familiar with to sort of highlight how this new data set has been used. And again, because of my own kind of personal bias, I focus really on the snow accumulation records because this is the area that I was most involved in. But also there's been a huge amount of work generated from the isotope compilations as well. So since the original databases became available, there's been multiple reconstructions. So the one, for example, here led by Yesen Wang and his group, looking down not just at the sort of regional, but then actually taking this even further into looking at the different drainage basins. And then some of this work has also been used to do numerous model evaluations. So looking at how the snow accumulation records actually compare with the reanalysis data. So a comparison just here is with the era reanalysis, the 20th century reanalysis. The same work has also been done looking at how this compares with the high resolution atmospheric climate model. So for example, the RECMO model. And some of the other work that's been done is actually comparing these with the larger models, the global circulation models. And this is really important for me because one of the main objectives with the Clevash group is that we were trying to engage not just the paleoclimate community, but we wanted to work with people working with a range of different archives. So whether that was ice cores or marine records, but it was really important that we also engaged with the modeling community. So those looking at the future projections and past paleo modeling, and also the observational scientists. And I'm pleased to say that this has actually been a really successful area. So there's been a number of new model data comparisons and data assimilations. And so Goose's group in Belgium have conducted a huge amount of research, and they're still incredibly active and lots more papers coming out. So I'm just going to go through a few of those ones. But essentially so this is some work by Quentin Deladin, looking at using the snow accumulation records, which are shown here in the black line, and comparing these with the range of surface mass balance that's simulated from a whole sort of suite of global circulation models. And so what we can see is that the surface mass balance trends between East Antarctica and West Antarctica are clearly stronger in the reconstructions based on the ice cores than they are in the global circulation models. And another sort of exciting thing that's come out of this comparison with the models is looking at actually how surface mass balance, which we sort of think of, snow accumulation, surface mass balance and precipitation, but it's actually linking these changes to temperature. So these plots here are showing the 5-yearly correlations between surface mass balance and surface air temperature in the different models. So this is looking at the global circulation models in A, and then looking more at the regional circulations in B, and then also comparing the surface mass balance and the surface air temperature, or the, in our case, the stable water isotopes from the Pages reanalysis. And so what we can see is that the reconstructions based on the ice core display a weaker relationship, indicating that the model data, there's a sort of discrepancy, if you like, between the model and the data. And this could be due to biases within the model, or it could be a combination, or due to the noise based in the ice core records. But the team used this to assimilate, so using these isotope-enabled models, and the output from that with the ice core data, generate this new data assimilation approach to create new surface air temperature reconstructions. And what they were able to show here, that is, on average, across the models, the relationship between surface mass balance and surface air temperature is often, or at least, sometimes is equivalent or even better than the relationship between stable water isotopes and surface air temperature. So that's sort of taking us a little bit outside of our comfort zone as a paleoclimate community, where we're often referring to stable water isotopes, delta 18O as our proxy for temperature. Whereas what some of this work has done is shown that actually the surface mass balance may be a more stable proxy for surface temperature. And there's some sort of reasons why this may be, and it may reflect the fact that the changes in stable water isotopes, as we detect in ice cores, are actually subject to quite large uncertainties. So linked to things, for example, like changes in precipitation seasonality or precipitation intermittency, and also changes in the moisture source origin. So the data assimilation approaches that have been done by this group have really confirmed the benefits of using not just a single proxy, so the stable water isotopes, but actually a combination of the two. So combining the surface mass balance and the stable water isotopes produces a much better and much more robust reconstruction of surface air temperature. The group then have taken this even further, exploring this relationship between surface mass balance and surface air temperature across the whole of the continent. And what they've been able to do is to see that in some areas, this relationship doesn't really work so well. And they were able to demonstrate that this is largely, or could largely be due to local wind-driven processes. So these are acting locally, such as wind redistribution, Föhn winds, or katabatic effects that actually overwhelm the kind of large-scale atmospheric contribution that's responsible for this positive surface mass balance and surface air temperature relationship. And so some of the work that Maria's done is looking at identifying regions where this relationship just doesn't work. And so on the figure here, you can see the correlations between surface air temperature and surface mass balance at the different ice core sites. And these grey shaded areas are actually indicating regions where this relationship seems to break down. And these are particularly kind of coastal regions or maybe mountainous regions. And so this is really useful. Again, it's kind of an example of how the data has been used by the modeling community. And then the modeling community, if you like, are handing it back to the data people by helping us to potentially identify where would be a good location for future drilling and where maybe we should be avoiding, but also some other interesting things to help improve our relationship. So for example, demonstrating that actually averaging ice cores over a short area can reduce some of this noise and actually improve the relationship. But some of the key things to take away from this is that we must correct for some of these local processes at the ice core sites, but also from the modelling side, it sort of highlighted that there really is a need still to improve the resolution of the models to better resolve these kind of smaller scale local changes and wind effects. So this data set has also been used in proposing this as a new proxy for open water. And so this is, again, sort of taking this snow accumulation data and looking at it from a slightly different perspective. And using it as a proxy for polynya. So these are these large open water areas within the sea ice or ice-free areas. And they're actually rarely observed around Antarctica. So during the satellite era, we actually have very few periods of which we can look at to see how frequent these polynyas occur. And so what this group have done is taken the snow accumulation records and sort of found a fingerprint, if you like, of what happens when we had the large polynyas in the Weddell Sea in 1974, 75 and 76. And this is what happens in terms of the snow accumulation or the surface mass balance. So this is reflected in a sort of positive surface mass balance around the coast of the Weddell Sea. And so this has been used as a fingerprint to take this back further in time to try and understand how the frequency of this open water has changed. And so this idea that snow accumulation is influenced by open water and hence sea ice changes has also been proposed in numerous studies looking at the relationship between changes in sea ice and changes in surface mass balance and snow accumulation. But it's really kind of useful seeing this on a continental scale, actually, how this snow accumulation could be telling us something about not just surface mass balance and how that affects Antarctica, but also telling us something about the wider climate variability and changes in sea ice. So in addition to the kind of changes in sea ice, these new compilations have actually helped us look a little bit more about what's driving the variability. So we know sea ice itself is dynamically linked to changes in ocean conditions, surface air temperature, but also in the surface, in the atmospheric circulation, so particularly in the winds. And so this is one of the spatial spatial reconstructions that Brooke and I put together following as part of Clivash. And what we were able to do is actually look at the large scale, how the large scale modes of variability are influencing surface mass balance. So what we can see here in these different reconstructions is the changes during the 20th century. So in the first plot, plot A, this is looking at the whole of the 20th century, and then just focusing in plot B in the second half of the 20th century, when things really start to accelerate. And so this is why we've got these darker colours. So the dark blues indicating big increases in snowfall, and then the darker reds indicating a big decline in snowfall. And what we found is that actually this pattern during the second part of the 20th century can be reproduced if we were just using changes in the SAM. So therefore, we were actually saying that 80% of this variability can be explained by changes in the southern annular mode, which is the largest mode of variability in the southern hemisphere. But changes in the SAM actually can't explain the trends that we've seen. And so if you take away the SAM picture, the SAM signal from this, what you're left with in plot D is the residual, or what's left. And this is the bit that can't be explained by changes in circulation. And this is the area that has to be being driven by another external forcing. So whether this could be changes in sea ice, or whether this is an underlying indication of atmospheric or oceanic warming. And in fact, the warming that's required to drive these kind of changes, the amount of warming required is consistent with what we saw in the Page's 2K synthesis for the isotope reconstructions. So this kind of leads me on to the second part of the talk, which is really, all of these different, the snow accumulation and the stable water isotopes provided a huge amount of information, but what we still are lacking is really what's driving this. And one of the key things that was identified as a driver for change is looking at sea ice. And so this was something identified as part of our workshop that we had in Cambridge in 2018. And from that, a group set up to look at whether we could produce longer reconstructions. And this is really important. I mean, some of the rationale behind this, if you like, is because sea ice has been pretty poorly represented in a number of the climate models. And there's been quite a lot of new research recently showing that actually these future climate predictions based on these climate models, the CMIP5 and the CMIP6 models, are actually strongly, the future outcomes are strongly dependent on the initial sea ice conditions. And so therefore it's really important that as a community, we're getting these initial conditions right. And so we really need to be looking at longer sea ice reconstructions. So this was another kind of example, if you like, of working across the different disciplines. So this was some work we did in combination, bringing together all the different sea ice proxies that were published from the ice core side, but also from the marine sediment side. And so there was a total of 92 sites that we were able to identify, and these were published records that indicated some change in sea ice during the last 2,000 years. And of those, the majority, 75 of those sites, were actually from the marine sediment cores. But as you can see, hopefully in the plots just here, they're actually quite poorly distributed. So there's sort of lots of records, but they're clustered around key regions. Then on the other hand, we've got the ice cores. There was only 17 ice cores. But as you'll see on the map here, this has got these kind of long tails from where the ice core sites are. And this is because essentially the two records are capturing two quite different things. So the marine records are capturing changes in sea ice directly in the ocean above it, whereas the ice cores are actually capturing changes in sea ice at the sea ice edge, which may be quite some distance from the ice core itself. And perhaps an easier way, or a sort of more complex way, if you like, depending on how you're looking at it, is looking at this schematic here of the differences. And so this kind of figure that Claire put together really highlights all the different proxies that are available to us as a community to reconstruct sea ice. And so from the ocean points, we're looking at is the marine snow that comprises of the dead organisms or any of the other particles that fall through the water column and eventually end up in the sediments. And so some of the key areas from this would be looking at diatoms. These provide an excellent potential for reconstructing sea ice conditions in the water above, or from looking at the geochemistry, so the foraminiferous shells. And then there's also been quite a lot of advances recently looking at more organic specific compounds. And so this is sort of telling you something about whether the presence or absence of sea ice above the sediment. For the ice cores, however, they're actually capturing a huge amount of changes that are being transported to the ice core site from across the whole region. So, for example, there's sea salt aerosols, and these can mainly be in the form of sodium. and Diana will explain a little bit more about this later, or from the halogens. So we've got bromide, chloride, iodide, have all been linked to changes in sea ice. And these are transported from the ice edge or from the surface of the ice to the ice core sites on the continent. Probably the most well-known of the sea ice proxies from the ice core community is methane sulfonic acid, or MSA, and this is produced by algae at the ice edge. And this was one of the first organic compounds that was identified in Antarctic ice cores and has been used to reconstruct sea ice for a range of different studies. But the understanding or the research into organic compounds has increased quite dramatically recently. And there's also some promise from other organic compounds, for example, oleic acid, which is a fatty acid found in marine diatoms measured in ice cores. And this was some work we've done looking at the Bouvet Island ice core. And if you'll permit me, I'm just going to use this as a good opportunity or excuse to highlight some work from my past and present students. And this is the map here showing Bouvet Island. So that sits right up there in the middle of the South Atlantic. And some work we've done there looking at new proxies for sea ice, looking at this oleic acid, showed how well it captured changes in sea ice. And so the Bouvet Island is only a 14-meter ice core. It's very short. It only goes back to 2001. However, it's given us a really good opportunity to explore all these different proxies from the same archive. So here's showing how the oleic acid compares with sea ice at the ice edge. But the other new proxy that I'm introducing here is the marine diatoms themselves. So this is some work from Dieter Tetzner, where we're actually looking at the diatoms contained in the ice core that have been blown there by the winds. And they're a sort of secondary measure confirming that marine diatoms, either looking at them chemically in the oleic acid or looking at them physically as counting the number of diatoms in the ice, are also a new and exciting proxy for sea ice. So some of the aims of the paper were combining the marine and the ice core records, because the idea is if we could combine the two records, we might be able to increase the temporal range of these ice core reconstructions, or sorry, these sea ice reconstructions, or increase the geographical range. And so it was important for us to see if there was ways in which we could combine the two records. And so first of all, kind of going through some of the advantages and disadvantages of using the two archives. So for ice cores, these are normally very high resolution. So this can be down to seasonal resolution. And this is great because it means that we can calibrate with the instrumental or the satellite records. However, the downside of a lot of the ice core records is that they're actually quite short. They're confined to the coastal regions, which means that they may only go back the last few decades to a few hundred years. So on the other side, the marine archives provide this much longer timescales, and in some cases they are able to also get down to annual resolution. However, often the chronological controls on the marine archives are less well defined, and very few of them actually overlap with this instrumental period, so we're not able to sort of do this calibration as we are for the ice cores. But what we really found is that neither archive provides the full spatial coverage over the last 2,000 years that we were looking for. However, there are some areas that we identified with these circles here, so particularly the Antarctic Peninsula or the area around the Ross Sea. These may be areas where we have enough high resolution marine and ice core records that we could start to do a proper multi-proxy reconstructions. So although we weren't able to establish a continent or a sort of hemispheric scale sea ice reconstruction over the last 2,000 years, as we aimed to do, we did find that there wasn't sufficient for that, but there was sufficient data that we could do a reconstruction during the 20th century. And this is primarily from the ice core records. And so these ice core data have been calibrated against the satellite observations to allow us to estimate the relative change in sea ice extent so that we could compare it with the changes that we're seeing during the last few decades. So what we found is that sea ice in the Ross Sea has been advancing, so these purple colours, since the beginning of the 20th century. And this sort of increasing trend is consistent with what we're seeing since the 1980s, during the satellite era, because it's the Ross Sea that's been experiencing the largest of all the regions, this large increase over the last 40 years. Another area where we have similar agreements between what we're seeing during the satellite era and over the 20th century is the decline in sea ice in the Bellingshausen Sea. And so this is the blue area, blue-green areas on the map here showing a decline. And so the rate of decline during the full 20th century, or 1900 to 1990, is broadly similar to what we've been seeing during the satellite era. So this indicates that this is part of a longer term trend. However, we did identify areas where there is differences. So particularly for the Weddell Sea, for example, is an area that during the satellite era, we've seen this expansion, whereas the proxy archives seem to suggest that during the period up until 1990, this area was experiencing a decline. So it's not unusual that we would, we wouldn't necessarily expect everything to match up perfectly. And it could just be that, this is a reflection of the large amount of variability in sea ice in these regions. So hopefully I've kind of given you a good overview of some of the science that we've done so far, and hopefully highlighted the importance of sea ice, and despite our best efforts, demonstrated that there's still a long way to go in terms of these sea ice reconstructions, which in some ways hands over nicely to Diana, who's then going to tell you about our latest data compilation. So let me just give Diana permission.
Yep.
Okay.
Right. I wonder
Have you got control?
I can control your screen indeed. Oh, all right. Wonderful. It works. more and more new technical features in Zoom. All right. Hello, everybody. Thank you for joining. And yes, indeed. So far you have nicely seen in this talk that despite a huge effort by the community, they were only reconstructions of the past sea ice extent covering past 100 years, or a little bit more than 100 years, and obviously at least the 20th century was a century already affected by the anthropogenic influence, and it would be so valuable and so great to actually have the data and have a robust reconstruction of past sea ice extent, and preferably past atmospheric circulation to compare actually anthropogenic influence and something in pre-industrial, which perfectly fits to the scope of pages 2K, and particularly Clavash 2K group, which aims to reconstruct climate variability in Southern Ocean and Antarctica over the past 2,000 years. So lately, about half a year ago, we have organized a data call, and we were nicely surprised to receive such a great feedback from the community submitting that many data, namely 111 ice cores containing data on sodium and sulfate. And the particular thing about this data call was that we actually involved 11 unpublished data and 11 unpublished data sets, because in the previous efforts, such as snow accumulation, data compilation, and stable water isotopes, their condition was only to submit the published data, whereas here we clearly realized that with chemistry data such as major ion concentrations, it's not always the case that scientists measure it and always publish it. Sometimes you simply don't know how to interpret it and you just store this data for ages. But we wanted to collect this all to a nice data set in order to be able to reconstruct past sea ice, and along with the previous effort of compiling snow accumulation and stable water isotopes, we will hopefully be able to also reconstruct atmospheric circulation, which is important in our understanding how this marine aerosol is brought to the continent and imprinted in ice cores. So we would like to acknowledge everybody from the community who have contributed data so far and who participated in the data processing. It was just enormous effort, and we didn't expect that we would be able to collect so many data, but also we are pretty happy that quite a few of this data span the full 2,000 years, and you can see it on the map here highlighted in yellow dots. So yep, and it's obviously it's really important for our for our reconstruction that we would have some grounds to actually interpret the data, and for that we need to compare sodium and sulfate concentration with satellite observations to actually be able to understand what to represent in ice cores. And from this perspective, our data set is also brilliant in a way, because we have just a few records, they're highlighted here in blue, which do not overlap or end up before 1979, and everything else we can compare with the existing satellite observations and reanalysis data, which is absolutely great. So the records span, quite a few of the records span full 2000 years, and obviously we can expect that some of the coastal data would be shorter, and inland data or inland records will be longer. So you can see here on the map the oldest year of the records, and black dots are something which starts in between year 0 to year 850, and light yellow dots are only recent records spanning past a few decades. Oh, of course, it's important to say, so we have focused our data pool only on sodium, sulfate, and on their concentrations, and where possible on fluxes. So fluxes is just concentration divided by accumulation rate, and given the past effort with the accumulation rate, it also gives us a good hope that we can actually fulfill this missing data. Why these two parameters? Simply because sodium has been proved as a pretty robust representative of the sea ice extent. The only question about sodium, whether it comes from the open water source or whether it comes from the snow on the sea ice, and we will see later that we actually have quite a surprising result. And with the sulfate data, so first of all, yes, sulfate has sea salt and non-sea salt sources, but also sulfate is a great indicator of absolute dating, because you all know that sulfate spikes are used as volcanic spikes, which will allow us also not only to check, but if needed, to synchronize the data scales. And here we just represented the average concentrations of both sodium and sulfate and their concentrations of fluxes over the past 40 years, just for the sake of comparison with actually satellite observations. And what we expected to see is actually to have like really large concentrations in the coastal areas and smaller concentrations in inland areas. Which is true to some extent, but not always. So this data set actually reveals many more surprises and not so obvious patterns as we expected it to be. With the sulfate, you can see that the distribution is even more odd. Well, possibly because here we showed a total sulfate concentration, did not divide it here to sea salt and non-sea salt. With fluxes, with sodium flux, it was more or less, we can more or less explain why we have bigger concentrations here on Antarctic Peninsula and in West Antarctica, simply because this area is sort of a gateway to the whole moisture coming to Antarctic continent. That's why the flux here is bigger. But with sulfate fluxes, the picture is not really obvious. And also, yeah, we have to acknowledge a big data gap in East Antarctica, which possibly we will fill in later. And as for the data interpretation, so we attempted to correlate the data with various satellite and reanalysis parameters. So here, for instance, you can see a correlation for Ferrigno-site. It is here on Antarctic Peninsula, notified with yellow circle, and we have taken sodium concentration for this point and carried out a correlation with sea ice concentration, and it's shown here with the color bar. Green color represents areas with positive correlations with sea ice concentration and sodium, and brown areas represents negative correlation. with arrows, we try to show the wind vectors and predominant circulation, where we observe significant positive correlation. Also, the areas and red and blue contours represent the geopotential height. Red stands for positive correlation, and blue stands for negative. So our what we are currently doing with our data set is that we try to carry out as many, we try to build as many spatial correlations as we can based on the available data, and I mean available iScore data, because obviously it's much easier to get satellite observations and reanalysis data. And just as a short, I don't know, either spoiler or review, we can tell that far not all sites represent the obvious correlation. So which means that this data set possibly will not allow us to conclude that, for instance, this site would represent a particular sea ice extent in this area. That is not always the case. The interpretation is much more complex than just a simple correlation with atmospheric parameters. But nevertheless, we were just trying to kind of conduct the first analysis, and we're trying to look again at the sodium concentration. So here you can see a map. Sodium concentration, bigger circles represent bigger concentrations over the satellite area, and this is the kind of surface correlation with it. And we can see that even though the higher concentrations are sort of in Ross area and in coastal drowning mode land, all in all, the data correlates a bit better with Pelinskaus and sea, and a bit of Amundsen sea with a sea ice concentration there, which is kind of a big surprise. Not always correlation with the winds though. As for the fluxes, the correlation is a bit more obvious because at least the regions coincide with the bigger fluxes. For sulfate concentration, well, again, it's not obvious because the sulfate concentration itself is a bit more well distributed, not so inland wise or coastal wise. So we need to look in a bit more details to understand the sulfate concentration better. And for the flux, it's the same conclusion, that it's much more complex than just a simple obvious correlation. Nevertheless, we are tempted to, if sulfate requires much more interpretation, but at least we used sulfate to check out our timescales. And yeah, we have to admit that all the data set, which consists of 111 iScore data sets, all this data set is compatible in terms of its timescale, because all the records were updated to the most recent waste divide 2014 timescale. And we have also seen a proof of it when we compared when we stacked all sulfate records, and we saw that the spikes actually coincide within 1 or 2 years, which means that at least for the tie points, for the absolute dating, we have very compatible timescales, which would increase the accuracy of our stack records. And even though things are not so obvious with sulfate record, nevertheless, we're attempting to make a 2,000 years long stack record of sodium concentration. So here you can see sodium anomalies over the past 2,000 years. So this year is 0. That's our current 2021 is here. What we can see is that over pretty much all first millennia, the concentration of sodium represented like weak negative anomaly. And the thing is that here, even though we knew that there were a few periods of like warmer and colder, like late antique little ice age, like Roman warm period and so on, but it's not so bright, let's say bright expressed, or not so prominent here, at least in the sodium records. But what we definitely can see is a trend to increasing positive sodium anomalies around year 1200, and even more bright expressed, something which is called Little Ice Age. Yes, of course, Little Ice Age was more or less not, well, it wasn't, it was proved that it was not evenly distributed over Antarctica, and probably was not present in all the Antarctica secrets. But in our stack record, we can see that during the Little Ice Age, we definitely observe a statistically significant positive anomaly. But the next interesting thing about this record is that over the 20th century, we can see a certain decline in sodium anomaly, which if we build let's say spatial correlation map of our stack record based on a few ice cores which span the full 2000 years, and they're notified here on with yellow circles. So if we build a spatial correlation map of this stack record with sea ice concentration, with geopotential height and atmospheric circulation in Antarctica, we see this picture, which means that at least for the period which covers satellite era observations, which means it's this period on the record. So this decline at the end of the 20th century, beginning of the 21st century, decline in sodium concentration correlates positively with a trend in sea ice concentration in Bellingshausen Sea and a bit of Amundsen Sea area, as well as Indian Ocean sector, which means that in our stack record at least shows some correlations with declining sea ice trend, and because the correlation is positive, it means that the major source of sodium for our stack record is salty snow or snow on the surface of sea ice, not the open ocean source. But this is of course an ongoing work. It's just first results. All right, so I hand over to Lise to summarize.
Couldn't get control of my mouse to unmute myself there. Right, I think I've got it again. Okay, brilliant, thank you. So just to kind of very quickly, I'm just going to put these bits up on here. Is hopefully the aim of this talk was to just kind of overview some of the work that we've done as Clevash 2K over the last 3 years. And we've generated lots and lots of research, but I just kind of want to say there's still more to do. We highlighted the potential to combine the marine and the ice core sea ice proxy records, but again, there's still a lot more to do. And really, it was great to see the kind of first results from this new data compilation, but again, finishing that saying there's still more to do. And this is really more for the benefit of the Pages 2K coordinators and Pages as a whole, that this area hasn't finished. So we want to keep working on it. I'm just going to put up as our final slide to say about our special issues. So we had a special issue in 2019 in geosciences, where we had 9 great publications. And because we had a good response to the first volume, we actually now have the second volume, which is live. So the deadline for that is December 2021. So if anyone's got any papers that relate to any of the topics we've talked about today, or anything to do with Antarctic climate variability or Southern Hemisphere climate variability during the last millennia or timescales within that, then please consider submitting to the special issue. Okay, thank you.
Thank you so much.
Would you like me to unshare the screen, or?
That would.
There we go.
Okay, I'm not sure
I'm
why.
so sorry. We had, yeah, a perfectly timed garbage truck to be as loud as possible just as you were finishing. So thank you so much. That was really, really wonderful to hear about all of this work. We can go ahead and open it up to questions now. So if there are any questions from anyone who is in the audience right now, go ahead and you can either unmute yourself and just ask directly, or if you'd like to type in a chat, you can do that as well.
if no one else will, I will start. So the sodium stack, the thing I had to think about was that would probably allow to get us a better understanding of orbital influences on Antarctic climate, wouldn't it? To get a good estimate on orbital trends there.
The sodium looking at orbital changes.
The stacked records, this record over the 2000 years.
Yeah, I'm not sure how large the orbital changes would have been over the last 2000 years. I mean, certainly for the longer time scales, that's something that would play an important part. But I think over these kind of time scales, I think what the sodium stack is going to be telling us is more about changes in atmospheric circulation and hopefully also changes in sea ice.
Okay, thanks. Any other questions?
That's fine. If nobody has any questions, that's fine. But if anybody is interested, or if anyone watches this out of hours, because that's the way we do things now, please do get in touch either with myself or have a look at the pages webpage for the Clevash group and get in touch with any of us, or yeah, please do get involved.
I have sort of a big picture question. It's because it's so exciting to see these different methods for reconstructing sea ice, which is such a holy grail, right, for the climate system. I'm just wondering if you've, from a data synthesis perspective, if you've encountered major challenges, or are there any major obstacles that you see to trying to combine these different types of proxies for sea ice? Because they're clearly going to be tracking slightly different things. What do you see as being the challenges over the next few years?
I think the major challenge at the moment is actually finding the records that are in close enough proximity to be able to compare them. And so what we, I think, kind of a little surprised that there are some areas and there are some sort of little pockets where there is really good high resolution marine records, and we've also got the ice core. So I think that's where we first of all have to sort of target. But you're right, they are speaking different languages, and that was why it's quite important to look at all the different proxies and see what they're telling us. And we were able to, look particularly at the, I think the organics, for example, and the diatoms is something that's a very new area of research in both the marine and the ice core side, but it's something that is picked up in the two records. And so I think that's probably going to be the most promising area, I think, combining those new proxies. Because you are comparing the same thing, just that they've reached the sites in different ways. So yeah, we have actually Claire Allen and I have a new PhD student starting in the autumn, and I'm really following on from this work. Her PhD is going to be about trying to look at ways of combining the marine and ice core records. So hopefully we'll make some advances in that area.
Yes,
Great.
may I have
Really
may I have a question to Diana? To the sodium 2000 data, please. Is that data are the results of the all synchronization using this sulfate data?
Well, no. I mean, there was no need to synchronize them because all the used records from Clevash 2K data call. So I only used, I think, like 13 records which span the full 2000 years, and these records, they've been already on a pretty robust time scale. So I think maybe I didn't put it right in the wording, but the reason, what I wanted to say, what I just wanted to notify that when we built together, when we put together all the sulfate records, their peaks, which notify volcanic peaks and thus absolute dating, they were all in line, which means that the timescales were already pretty good. And as was, as was concluded by the working group led by Michael Siegel, that actually things, most of the records were up to date to the Wave Divide 2014 timescale. So there was no need to synchronize them. They are already on a very good timescales.
I see. Thank you.
All right, well, we're approaching the end of the hour, so let's, I am applauding, and you can just envision the silent thunderous applause from all of our attendees. Thank you so much. This was a really, really excellent talk, and especially to kick off our new seminar series. So we really appreciate your sharing all of this information with us.